2021 Grade 12 AMC 12A Fall Questions 11 through 20. Problem number 11. Consider two concentric circles of radius 17 and 19. The larger circle has a chord, half of which lies inside the smaller circle. What is the length of the chord of the larger circle? So let's draw the diagram and let's discuss this. Alright, so this diagram is going to hopefully help illustrate the question. So we've got A, B, C, D. I'm going to label that as follows, and then this is the center of the circle. Let's call it O, and then this part we'll call M, this dot right there. Okay, so we know, according to the question, that AM is equal to MD. And then in this triangle OMA, we can figure out a Pythagorean relationship, since this is a right angle and that line is just perpendicular to the green line. The black line and green line are perpendicular. So simple Pythagoras, OM squared plus AM squared is equal to OA squared. And then some of this we know OA is the radius, which they told us is 19 in the question. OM, I don't really know much about, but AM, I do know, is the full length, which is AD, divided by 2. And that's entirely from the question stem. Okay, so then that means that OM squared would be 19 squared minus AD over 2 all squared. Got it? And then in a very similar way, we're going to do the same kind of thing on triangle OMB. OMB this time, the smaller triangle. From that one, we get that OM squared plus MB squared is equal to OB squared. Well, OB is 17, and then OM, I'm not going to do anything to change that, but MB, I know, is BC divided by 2, because that line that goes top to bottom is essentially just a bisector, the way I drew it. So there we go. So this gives me that OM squared is 17 squared minus BC over 2 squared. Correct? So now we have something for OM here, something for OM there, and we can equate them. So let's equate those two. That means that 17 squared minus BC over 2 all squared is equal to 19 squared minus AD over 2 all squared. Okay, so now let's work with this here. We got AD over 2 all squared minus BC over 2 all squared. And on this side, we got 19 squared minus 17 squared. Now keep in mind, or recall, that BC is equal to a half of AD from the diagram up here. BC is equal to half of AD. That's actually from the question stem. Not even, I mean, you don't even need to look at the diagram. Just my diagram was just trying to mimic what the question stem was telling you. So that means I can put that in and put AD over 2 all squared and minus BC, which is AD over 2, all over 2 all squared. And this is 72. Got it? Okay, so now we just have AD squared over 4 minus AD squared. This is going to be over 16 is equal to 72. Top and bottom by 4. And then we get 3AD squared over 16 is 72. And therefore, AD squared would be 72 times 16 over 3. And that's 24 times 16, which is 384, which is 64 times 6. And therefore, AD would be the square root of that, so 8 root 6. Yeah, 8 root 6. And AD is what they wanted us to figure out, which is the length of the entire chord. And there you go, 8 root 6. So the answer is E. Problem number 12. What is the number of terms with rational coefficients among the 1001 terms in the expansion of x times the cube root of 2 plus y times the square root of 3 all to the power of 1000? Okay, So what we need to recall is something that is called the binomial theorem. And some of you may remember it, some of you may not. That's okay, I will write it out. If you have the expansion of some polynomial called x plus y to the power of n, it is calculated as follows. It's the sum from k going from 0 to n of n choose k times x to the power of n minus k times y to the power of k. Now, that may seem a bit confusing if you've never seen this, but let's give an example. Let's say you have x plus y to the power of 10. Using that formula, it would be the sum from k equals 0 to 10 of 10 choose k, x to the power of 10 minus k, y to the power of k. Now, I'm not going to write out all of them, but let's just write out a few. When k is 0, this is 10 choose 0, x to the power of 10, y to the power of 0. When k is 1, it becomes 10 choose 1, x to the power of 9, y to the power of 1. When k is 2, it becomes 10 choose 2, x to the power of 8, y to the power of 2. Plus dot dot dot, keeps on going. Let's just do a couple more. When k is 9, it's 10 choose 9, x to the power of 1, y to the power of 9. And when k is 10, it's 10 choose 10, x to the power of 0, y to the power of 10. And then, of course, you simplify what is 10 choose 0, what is 10 choose 1, what is 10 choose 2 to fill in the coefficients. Okay, so that's basically what we're going to do, but we're not doing it with x plus y, we're doing it with this weird thing that they gave us that I will have to expand using the binomial theorem. So that would basically be the sum from k going from 0 to 1000 this time of 1000 choose k. And then our first term is x, the cube root of 2, all to the 1000 minus k. And then there will be the next term, which is y times the square root of 3, all to the power of k. Okay, that's basically all it is. All right, so let's see what we can get when we try to expand and simplify. So this is going to be the sum from k equals 0 to 1000. 1000 choose k, and x to the power of 1000 minus k. This is the cube root, right? So it's 2 to the power of 1/3, correct? Yeah. So that means it'll be 2 to the power of 1000 minus k over 3. And then this guy, y to the power of k, and then that's the square root of 3, which is 3 to the power of a half. So it'd be 3 to the power of k over 2. Okay, so hopefully I did that correctly. And then now what is the question wanting us to do? They want coefficients to be rational. So we want the exponents to be integers. That's the only way we're going to get rational numbers. So let me write that out. So this is sort of the rule we are going to follow to try to figure out this question out. And therefore, this exponent here and this exponent here, we want those to be integers. So from this guy here, k over 2 has to be an integer, so that means k must be even. That's the only way that's going to become an integer, correct? And then from that guy there, that means 1000 minus k over 3. For that to be an integer, that means 1000 minus k must be a multiple of 3. Correct? So let that sink in. All right, so let's go here. Let's try to figure this out. K is going from 0 to 1000, right? So that's our range. So k has to behave in this way. So let's concentrate on that first, and then I'll concentrate on that. Concentrating on this guy first. Well, if 1000 minus k is a multiple of 3, k is going to be 1 or 4 or 7 or 10 or 13 and so on. And you can plug those in to verify that it will indeed make this statement hold true. 22, 25, and you get the point. So dot, 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 all the way till 994, 997, and 1,000, right? Because k is going from 0 to 1,000. Okay, so these are the numbers that k will equal if this is satisfied right here. But we also have to satisfy this guy. K must be even, so we can only take the even ones. Got it? Okay, so now we have to add them all up. Well, I think if you just looked at all of these numbers, it was every third number, correct? From 1 to 1,000, so that's 334. Yeah, and then I circled half of them, as you can see. So 334 divided by 2, which is 167. So k has 167 possible values to satisfy the requirements of the question, and therefore number 12 is C. Problem number 13. The angle bisector of the acute angle formed at the origin by the graphs of the lines y equals x and y equals 3x has the equation y equals kx. What is k? So let's first draw a diagram to illustrate what is it that they're asking. They want you to first draw the lines y equals x and y equals 3x. So y equals x is going to be pretty much like that. Y equals 3x, well, something like that. Okay, approximately. And then you've got this new line that they're saying is y equals kx, and it cuts the angle in half that these two black lines make. So that means that is going to be something like that, approximately, right? So this is y equals kx, and this was y equals x, and this was y is equal to 3x. Okay, so now let's label these angles. This one I'll just call alpha. This one is alpha because, you know, that line cut that angle in half. So alpha and alpha. This angle I'll call theta, and this angle, well, that's 45 degrees, right? Because it's y equals x basically goes right down the middle of the 90-degree angle that is created by the x and y axis. Okay, so that's a pretty decent start. Now, without making this diagram messy, I'm going to concentrate on a few things. We're going to draw a little triangle here. I'll draw the triangle over here to illustrate. Now, that triangle, we know for sure, has a ratio of 3 to 1 because it's basically formed by the line y equals 3x. And then I had labeled this angle theta. So that means that the tan of theta is equal to 1 over 3. Right? Nothing fancy so far, just basics. Now let's do the same thing, but this time let's use that triangle right there, where this is a right angle. That was a right angle too, by the way. And similarly, let's draw that triangle over here. Actually, it'll be something like this, right? And then now we know that this ratio is x to kx because it's formed by the line y equals kx. And then this angle in here is 45 plus alpha. So the tan of 45 plus alpha will be equal to kx over x, which is just k. Got it? Okay. Now, all of these angles equal 90 degrees. So that means theta plus 2 alpha plus 45 is equal to 90. So that means theta plus 2 alpha is equal to 45, and therefore theta is equal to 45 minus 2 alpha. So I can substitute that in here. Instead of tan theta, I just put tan of 45 minus 2 alpha is equal to 1/3. So that's a pretty good setup. This equation right here and this equation right here. Those two are going to be used to figure out the answer to this question. So a little knowledge of some trig identities will be required, and those trig identities are essentially the tan trig identities. So first let's start with that guy up there that says tan of 45 minus 2 alpha is equal to 1/3. Correct? And if you remember the trig identities, this is the tan of 45 minus the tan of 2 alpha all over 1 plus tan 45 tan of 2 alpha. And that's 1/3. The good news is that the tan of 45 is 1. So this is 1 minus the tan of 2 alpha over 1 plus the tan of 2 alpha. And then we just use some basic algebra here to, cross multiply all that stuff. So that would be 3 minus 3 tan 2 alpha is equal to 1 plus 2 alpha. 1 plus tan of 2 alpha, I should say. And let's see here, what does this give me? 2 is equal to 4 tan of 2 alpha. That means 1/2 is tan of 2 alpha. And, okay. Oh, and then I have to use a trig identity for tan of 2 alpha. I gotcha. So they're not making this easy for me. Okay, the tan of 2 alpha, that is what? 2 tan alpha over 1 minus tan squared alpha, right? And that's 1/2. So we got a quadratic here. Okay, so 1 minus tan alpha squared is 4 tan alpha. Okay, so this is a quadratic, so put everything on one side, and we get tan squared alpha plus 4 tan alpha minus 1. Okay, use a quadratic. So alpha would be, or actually not alpha, tan of alpha is going to be, what is it going to be? Minus b plus or minus the square root of b squared minus 4ac, correct? All over 2a. So this looks like minus 4 plus or minus root 20 all over 2. Okay. So that looks like to me minus 4 plus or minus 2 root 5 over 2. So that's minus 2 plus or minus root 5. Oh, we got 2 answers. Oh boy. Well, I'm going to go with the plus one. Just to, because I have to use one. I'm not sure which one to use, so I'm going to use this one first. Hopefully I'll be right. Okay, now I go back and I use this formula, this one right here. Tan of 45 plus alpha is k. So the tan of 45 plus alpha is equal to k. And again, I use a trig identity. So you have the tan of 45 plus the tan of alpha over 1 minus the tan of 45 tan of alpha is equal to k. So 1 plus tan of alpha, 1 minus tan of alpha. There we go. Now we can plug in the tan of alpha without making any mistakes, hopefully. So we got minus 2 plus root 5. And on the bottom, it will be minus, same thing, 2 plus root 5. And just when you thought you were finished, you still got to rationalize the denominator, because they don't like roots in the denominator. So the top will become root 5 minus 1, and the bottom becomes root 5 plus negative root 5 plus 3. Okay, so I got to multiply top and bottom by 3 plus root 5, correct? Yeah, 3 plus root 5. Okay, we're getting there. So that makes the top equal to, let's see here, 3 root 5 plus 5 minus 3 minus root 5, and the bottom will be 9 minus 5. So that means we have 2 root 5 plus 2 over 4, and that is root 5 plus 1 over 2. Root 5 plus 1 over 2 is the value for k, and let's see what we get. What is k? Root 5 plus 1 over 2, and that's choice A. So it's an excellent question. Problem number 14, I should say. In the figure, equilateral hexagon ABCDEF has three non-adjacent acute interior angles that each measure 30 degrees. The enclosed area of the hexagon is 6 root 3. What is the perimeter of the hexagon? So first I have to sort of connect some lines here, like that. And let's label this, because of the fact that it's equilateral, it tells you in the question, all these sides are the same, so because it's very symmetric. So because it's very symmetric, that triangle BFD in the middle is going to be equilateral. So that means this is 60 degrees, that's 60 degrees, and that's 60 degrees. And therefore, because it's equilateral, these are the same, right? So these are isosceles triangles. And because they're isosceles triangles, then we can figure this out with those properties. And they help you out a little bit in the question stem. They say that the interior angles are 30. So that means this is 30 here. And that means that this would be 75 and this is 75. Because those two angles have to be equal. And they all have to add up to 180. So that helps out a lot. All right. Let's see what we can do here. I'm going to draw this triangle, this equilateral triangle here, like that, and then draw a line perpendicular top to bottom. Now I'm going to call that height, and I'm going to call this x and the base b, and this is right angle. This is 75, and that is 15 actually, right? Because it's only half the angle. So we're going to need this because the sine of 75 is therefore going to be h over x, and therefore x is h over sine 75, or whatever x times sine 75 is equal to h. Let's see what we get. And then similarly, cos of 75 is going to be b over 2, remember, just from there to there, over x, and therefore x is equal to b over 2 over cos of 75, or 2x cos 75 is equal to b. And yeah, so we have something for x here, we have something for x here, and we can equate them, therefore, that b over 2 cos 75 is equal to h over sine of 75. Now, let's see if that helps. I just wanted to put that in there. I'm not sure what benefit that will be, but let's see. Now, they told me that they want the perimeter, right? So the perimeter, according to what I wrote, I've made one side equal to x. Now, the perimeter is 6 sides, so the perimeter essentially will be 6x. So if I can figure out the value for x, then I'm done with the question. Now, they've also told me that the area is equal to 6 root 3. So area is equal to 6 root 3. Now, how do you figure out the area? The area, I think, is just easily figured out with these triangles. So we've got these three big ones that are isosceles. So 1/2 base times height for those ones. And there's 3, so put a 3 out front. And then we've got the equilateral triangle in the middle. And the formula for the area of an equilateral triangle is root 3 over 4 times the base squared. Got it? Okay, let's see what we can get here. This is going to be 3 over 2. The base is b, but b I have over here. So I've got 2x cos 75. And then the height I've got here, which is, it's going to be times x sine 75. And then root 3 over 4 b squared. B, again, I'm going to use that one, which is 2x cos 75 all squared, right? Because it's b squared. Okay, that's pretty good. It's going to be a lot of algebra, though. Now, the main problem, I think, is that this is 6 root 3. So that's helpful, very helpful. But the problem is that we've got to figure out x, which shouldn't be a problem. However, we just got these coses and sines, and we're not allowed to use a calculator. If you could use a calculator, piece of cake. But we're not allowed to use a calculator. So what we have to do is figure out the values of cos 75 and the value of sine 75. Okay, that's where your trigonometry identities come in. Remember, it's cos 30 plus 45, and then you remember this is going to be cos 30 times cos 45 minus sine 30 sine 45, and then the cos of 30 and the cos of 45 you should have memorized. Root 3 over 2, root 2 over 2, and then minus 1/2 root 2 over 2. And when you crunch out all these numbers, you get root 6 minus root 2 over 4. And similarly, sine of 75, same thing. I'll let you do it. Same thing. You use a trig identity, and you will get root 6 plus root 2 over 4. Got it? And then you just plug it back into here. So 6 root 3 would be 3 over, well, actually 3. Let's see if we can do this without making any mistakes. X squared, and then we've got the cos of 75, which is root 6 minus root 2 over 4. And the sine of 75, which is root 6 plus root 2 over 4. Correct? And then I've got to look at this guy, which is root 3 over 2 this time. And we have x squared, right? X squared. Actually, it's root 3 because this 2 is going to be squared. So I can get rid of that. And then I just got to put in the cos of 75, which is root 6 minus root 2 over 4 all squared. And I believe that's it. I think unless I made a mistake, this should be the way to do it. Okay, so 6 root 3. All right, so that's good. And then I'm going to factor out the x squared, since there's an x squared in both of those. And then this is going to be 3. And then expanding that works out to be 6 minus 2 over 16. Okay, things are working out pretty nicely already. And then this next guy, let's see, root 3. And then when you expand that, you get 6 minus 2 root 12 plus 2 over 16. Okay. So this is x squared. Let's see here, 3 over 4, so that's nice. And then this one, let's see here, root 3, 8 minus 4 root 3, I believe, over 16. So for 3 over 4, and then we've got 2, I should say. 2 minus root 3 over 4. Correct? Okay. All right, and let's not forget that 6 root 3, because that's obviously very important. So let's see if we can combine this. The denominator looks like 4, so that's going to be 3 plus 2 root 3 minus 3. And therefore, this is x squared. Oh, this works out very nicely. The 3's cancel out, so it's just root 3 over 2. Yeah. Let's see here. Yeah, that's it. Sometimes I second guess myself. Okay, so the root 3's are going to be gone on both sides, and then the 2 can come up here. Oh, great. X squared is 12. So that means x is what? The square root of 12, which is 2 root 3. And then to get the perimeter, we needed 6x. So that's going to be 12 root 3. Yeah, so 12 root 3 is the answer. And therefore, that would be, oh, where are the answer choices? Oh, they're down here. That's E for this question. Problem number 15. recall that the conjugate of the complex number w is equal to a plus bi, where a and b are real numbers, and I is equal to -1, is the complex number w prime, which is a minus bi. For any complex number z, f at z, let f at z equal 4i conjugate of z. The polynomial has 4 complex roots. Let q at z equal that, whose polynomial roots are f at z1 to f at z4, where the coefficients are a, b, c, and d. What is b plus d? Okay, so this seems at first a bit confusing, so let's talk about this. W, according to their definition, or any definition, is a plus bi. It's just a complex number. Okay, the conjugate, w prime, whatever you want to call it, a minus bi. And then they are giving us a special function that f at z would be 4 times I times the conjugate of z. All right? And then they've given us another polynomial, z to the power of 4, 4z cubed plus 3z squared plus 2z plus 1. Okay, great. And then they've given us yet another one that is similar, but instead of actual number coefficients, they've given us letter coefficients. All right, no problem. And they've given us the roots. So for the first guy, the roots here are z1, z2, z3, and z4. For this qz, the roots are f at z1, f at z2, f at z3, and f at z4. Got it? Okay. So that is the heart of the question in terms of the setup. Now, what we have to do is we have to figure out a way of figuring the coefficients a, b, c, and d. And that's where we use something known as vietas. And some of you are familiar. If you're not, I'll give you the basics. Let's say you have a very basic polynomial, ax squared plus bx plus c is equal to 0. Vietas tells me that the sum of the roots of this polynomial can be calculated very simply with the coefficients minus b over a. And the product of the roots is also calculated easily with just c over a. Got it? Now, this vietas also works for higher degree polynomials. So this was just a polynomial that's squared. So what about if you had a polynomial to the 4th power, like this one, ax to the power of 4, bx cubed plus cx squared plus dx plus e. Same thing. This time, the product and sum can be calculated as follows. The sum of the roots is the same calculation. Product of the roots, e over a. Got it? So, similar. So, let's use vietas. Sum of the roots for the first guy up here is z1 plus z2 plus z3 plus z4. Now, according to vietas, it would be this e over a, which in this case looks like, to me, 1 over 1, which is just 1. Or, sorry. The sum, I got to make sure you don't make it, you don't confuse them. The sum is up here. Sorry, minus b over a. So that would be minus 4 over 1, which is minus 4. Okay, got it? All right. Now the product, okay, now we can, since I'm so excited to use that one, now I can use the product. That's multiplying them all. That's going to be the e over a, which is 1 over 1, which is 1. Okay, all right. So you get that, right? Okay, so you do the same thing with the q is z. Now, vietas, there's one more. It's called the sum of the products. Sum of the products. And you say, well, what do you mean by sum of the products? Sum of the products is like z1 times z2 plus z1 times z3 plus z1 times z4 plus z2 times z3 plus z3 times z4 plus z3 times z4. Let's see here. z1 times z2, z1 times z3, z1 times z4, z2 times z3, z2 times z4. That should be a 2, and then z3 times z4. So this is what's known as the sum of the products. And that also can be calculated with a nice formula, c over a. Okay? So in our case, c over a would be what? And this guy up here, 3 over 1, which is just 3, of course. Okay? All right. So we are going to do the same thing, but this time with q of z. Q at z. So q at z right here, same thing. The sum of the products. So that's basically f at z1 times f at z2 plus dot dot dot, all these guys, right? The sum of the products all the way to the f at z3 times f at z4. I'm not going to write them all out. And that's equal to c over a, right? And in this case, it would be b over 1. You got to be careful as to what is a, what is b. In this case, a is 1, and then b is a, c is b. It's a little confusing, but it shouldn't be so bad. Now, finally, we get to use the definition, which is actually just right here. What is f at z1? Well, f at z1, according to definition, would be 4i z1 conjugate. F at z2 would be 4i z2 conjugate, and so on. F at z3 would be 4i z3 conjugate. F at z4 would be 4i z4 conjugate, and this is equal to b. Got it? Okay, so now we have to use some of those laws with complex numbers. Okay, so before I use the laws, let's combine these guys. This is going to be 16i squared, and then z1 times z2, and both of those are conjugates. Dot, 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 all the way, 16i squared, z3 conjugate, z4 conjugate, and that's b. Now, here's the law. The first law is that if you have a conjugate times b conjugate, it is equivalent to a times b all conjugate, like that. So I'm going to use that law, and this is going to be minus 16, right? Because I squared is negative 1, and therefore this would become z1 times z2 all conjugate. Got it? And similarly, dot, 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 this would be also minus 16 z3 z4 all conjugate, like that. Okay, so it looks to me that b is essentially just minus 16, and then all of these are combined together like that. Okay, hopefully that makes sense without too much confusion. Now we have another rule. Another rule is that if you have a conjugate plus b conjugate, it's the same as a plus b conjugate, like that. Got it? So that means this b becomes minus 16 z1 times z2 plus dot, 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 z3, z4, the entire sum, all conjugate. Got it? Okay, so hopefully that is not a problem. Now, this guy here, just this guy, forget about the conjugate. I'm just going to circle the number, this part. That's already been calculated. This is essentially the sum of the products, which is right here. And we already calculated it to be equal to 3. So we put that in. But we're not just going to put 3. We're going to put 3 plus 0i, because I have to put it in the form of a complex number, because I have to take the conjugate of that. Got it? Now, what's the conjugate of 3 plus 0i? Well, the conjugate is 3 minus 0i, which is, I'll just write it in like this. Okay? But minus 0i is just 0, so this is just minus 16 times 3, which is b. And there you go. So b is negative 48. Now we have to figure out D, because they want you to figure out, I think, B plus D, or yeah. So D is, I think did we already figure it out? It's the product, right? D, yeah, D would be using Vietas on this guy. D would be the product, yeah, this one. So the product of the roots, which are these guys, which essentially would just be f at z1 times f at z2 times f at z3 times f at z4, would be this formula right here, E over A. So in this case, it would be D over 1, which is, of course, just D. So D is the product of those. So that's how we're going to figure out D. So D is f at z1 times f at z2 times f at z3 times f at z4, like that. Got it? And then we use the definition. So this is 4i z1, 4i z2, 4i z3, 4i z4. So this looks like 16 times 16, 256. I to the power of 4, so that's going to be 1. And then we've got this z1 times z2 times z3 times z4. But all of these are conjugates. Correct? And then we use that law again. z1 times z2 times z3 times z4, all conjugate. This product here we already figured out, just this guy right here. z1 times z2 times z3 times z4, I think we did right here. See this guy? Oh, no, sorry, this guy. That's just 1, so that's good. But I'm not going to put 1, I'm going to put the conjugate. I'm going to put it in complex form, so 1 plus 0i, because I have to take the conjugate of that. Well, the conjugate of 1 plus 0i is 1 minus 0i. And that's just 256, because this part, because 0i is just 0. So there we go. We got D. B we have, and D we have, so it's minus 48 plus 256, which I believe is 208. And that is D from the answer choices right here for number 15. Number 16, an organization of 30 employees, 20 of which have brand A computer, while the other 10 have brand B. For security, computers can only be connected to each other and only by cables. The cables can only connect a brand A to a brand B computer, and employees can communicate with each other if the computers are directly connected by a cable or by relaying message through a series of connected computers. Initially, no computer is connected to any other. A technician arbitrarily selects one computer of each brand and installs a cable between them, provided there is not already a cable between that pair. Technician stops once every employee can communicate with each other. What is the maximum possible number of cables used? Okay, so we've got 30 of these employees, and 20 are computer A, and the other 10 have computer B. So you can communicate or join an A computer to a B computer, and they want the maximum. So I thought, okay, well, the maximum number of A's is 20, the maximum number of B's is 10. So if you multiply them, because we have A1, A2, ... all the way to A20, and same thing with B's, you have B1, B2, ... all the way to B10. So the maximum would be, in terms of number of choices, 20 times 10, which is 200. But unfortunately, 200 is not one of the answer choices. Okay. So that means I got to rethink this. So what I did was I said, okay, let's isolate one of the computers. Let's not add it right now. Let's add it a little bit later. Let's isolate A1. And let's deal with the other 29 computers. Connect the other 29 computers. All right, so if I do that, then I've got, for A and for B, I've got 19 A computers and still have 10 of all the B computers. So 19 times 10 gives me 190. All right. But this 190 represents the number of ways I can connect all the computers from A2 to A20 with B2 to B10. Remember, I've isolated A1. And then once I connect all those guys, I've got to go back and connect A1. Then I have to have one final cable to connect that A1 that I had originally isolated. So I take this one final cable and add it to the 190, and that gives me 191. So that's the approach for this question, and that gives me choice B. Problem 17. How many ordered pairs BC of positive integers does neither x squared plus bx plus c equals 0, nor x squared plus cx plus b equals 0 have two distinct real solutions? So neither. Two distinct real solutions. So if you have no distinct solutions, what that means is that the discriminant is equal to 0. So b squared minus 4ac of a quadratic equation is equal to 0. If you have no real solutions, that means that b squared minus 4ac, which is the discriminant, is less than 0. So they're telling me that they don't want distinct and they don't want real. So that means that d has to be less than or equal to 0. Okay, so for the first equation, that's x squared plus bx plus c is equal to 0. The discriminant would be, let's see here, b squared minus 4 times 1 times c is less than or equal to 0. So b squared minus 4c less than or equal to 0, and therefore b squared is less than or equal to 4c. Got it? Okay, so then the next one is x squared plus cx plus b is equal to 0. Same story. Now we have c squared minus 4 times 1 times b is less than or equal to 0. So therefore c squared minus 4b is less than or equal to 0. So c squared is less than or equal to 4b. So here we go. That's the first one. That's the second one. Now we have to somehow combine those two. Let's see how I can do that. Well, I've got b squared is less than 4c less than or equal to. If I square both sides, I get b to the power of 4 is less than or equal to 16c squared. Okay. This one here, if I multiply both sides by 16, I get 16c squared is less than or equal to 64b. Aha, got it. Therefore, I can combine them like that. Did you see what I did there? Yeah, okay, so this is what I'm going to work with. This basically combines everything in the question. Now, the good news is they told me that b and c have to be positive integers, so that helps us out quite a bit. So basically, I have to solve that inequality with some positive integers. Okay, let's try b1. When b is 1, this becomes 1 less than 16c squared less than 64. So that looks to me that c can be either 1 or 2. Similarly, when b is 2, this becomes 16 is less than 16c squared is less than 128, and c therefore can be again 1 or 2. If b is 3, this means they have 81 less than 16c squared less than or equal to 192, so c is 3. And then when b is 4, this is 256 less than 16c squared less than 256, c is 4. And I think that's it. After that, it doesn't work. So my ordered pairs, BC, it looks like 1, 1, 1, 2, 2, 1, 2, 2, 3, 3, and 4, 4. So that's what? 1, 2, 3, 4, 6. 6 ordered pairs that satisfy these conditions, and therefore number 17, the answer is B. Problem 21. Each of the 20 balls is tossed independently and at random into one of the 5 bins. Let P be the probability that some bin ends up with 3 balls, another with 5, another with 3, and the other 3 with 4 balls each. Let Q be the probability that every bin ends up with 4 balls. What is P over Q? So they want the probability of P over Q. So P is the scenario where you have 3, 5, 4, 4, 4, the number of balls that goes into each of those 5 bins. And Q is the probability that you have the scenario where all the bins have 4 balls. Okay. All right, so let's first talk about one of these, and then hopefully you'll get an idea of how to figure this out. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, we got 20 balls, right? And we got 5 bins. But the first scenario is a 3, 5, 4, 4, 4. So we're going to have bin number 1 have the first 3 balls, and then bin number 2 will have 5, and then bin number 4 will have, bin number 3 will have 4, and then 4 in the next bin, and then finally that bin will have 4 as well. Actually, that's bin number 5. And the number of balls is indicated by the dashed lines. So that is a scenario of a 3, 5, 4, 4, 4 distribution. Okay, so now we have to figure out the probability of this. First, let's figure out the probability of right here. What's the probability, or how many ways can we put balls in that first slot? Well, there's 20 balls, so there's 20 different choices. Once a ball is placed there, we have 19 choices remaining for that one. Then 18 choices remaining for that one, and 17, and so on. So really, there's 20 factorial ways of doing that, of distributing all the balls. But it's obviously not that simple, because this double counts, overcounts. Actually, overcounts is the better word to use. It overcounts by a lot. So we have to divide by several things to ensure we don't overcount. So what do we divide by? How do we decide what to divide by? Well, keep in mind, I'll use a different color to show that this is going to be different now. If you just look at this scenario right here, 3 balls can be arranged in 6 different ways, right? The first ball of the 3 that goes there has 3 possible choices. Then the next ball has 2, and then the next one has 1. So as you can see, there's 6 ways of arranging that. So we have to ensure that those 6 ways are accounted for. And what you do is you put that in the denominator. In a very similar way, if you look at this bin, there's 5 balls that you have to put in that bin. The first ball, there's 5 choices. 5 choices for that first ball. And then 4, and then 3, and then 2, and then 1. So if you multiply all these guys, that's 120. Actually, it shouldn't be 6 factorial. Man, good thing I caught that. It should be just 6. Okay, so let's erase that 6, that exclamation mark. Okay, so it's 120 for that one. And then in a very similar way, this is going to be 4, 3, 2, 1. So that's 24 when you multiply it out. And these 2 guys are also 24 and 24 in terms of the number of different ways that we can arrange those balls. So this is how you figure out P. Okay? So hopefully that is something that is clear. In a very similar way, Q is figured out as follows. The top is going to be the same, but then we have to divide by a lot of numbers because we've overcounted a lot. And remember, this is now a 4, 4, 4, 4, 4 situation. So you're going to divide by 4 factorial 5 times, right? Exactly the same sort of system that I used to figure out So there you go. That's P over Q. So you've got this 20 factorial over 6 times 120 times 24 to the power of 3 all over 20 factorial. That looks like 24 to the power of 5. Okay. And when you invert and multiply, the 20 factorials interestingly vanish. So the only thing you get left with is 24 to the power of 5 in the numerator, and then 6 times 120 times 24 to the power of 3. And this looks like 24 times 24 over 6 times 120. And when you reduce all of this, the 124 I think can cancel. I think you have 24 over 30. Yeah, 24 over 30. And that is, of course, 5 over 6. I say, okay, we got down to 5 over 6, but all the answers are whole numbers. What happened here? Well, what happened is that, and this is a tricky question, is that there's something else that we needed to do when we calculated P. And that is, we have to take into consideration the following. This scenario, if you pay close attention, was I put 3 here, 5 here, right? 4 here, and then 4 and 4. That's just one possible way. You can also have, say, 5 in bin number 1, and then 3 in bin number 2, and then 4, 4, 4. You see what I mean? Or you could have had 4 in bin number 1, and 5 in bin number 2, and 3 in bin number 3. So all of those need to be considered. Now, how many of those? Well, in bin number 1, you've got 5 choices, right? You either put 3 balls, 5 balls, 4 balls, 4 balls, or 4 balls. So since you have 5 choices, 5 bins to put the 3 balls in. So say, where should I put the 3 balls? Here, I put them in bin number 1. But I have 5 choices. I can put the 3 balls in bin number 1, 2, 3, 4, or 5. So because I have 5 choices, I have to multiply the top by 5. And then the next one, which is, say, the 5 balls, right? Here I put them in bin number 2. But I've got 4 remaining choices for the 5 balls. I can put them in the 2nd bin, 3rd bin, 4th bin, or 5th bin. So because I have 4 remaining choices, I put 4 there. And then once that is allocated, the other 3 bins will automatically get the 4, 4, 4 distribution. So that 5 times 4, which is 20, has to be put there. And when you do that, then you get the proper calculation, and that is if you don't mess up the fraction, which I think I did. Sorry about that. This should have been 4 over 5. So you got to make sure you don't mess up the mathematics. So 4 over 5, and then finally, if you multiply that by 20, it'll be 16. There we go. So hopefully that wasn't too bad. 21 is E. Number 19. Let x be the least real number greater than 1 such that sine of x is equal to sine of x squared, where the arguments are in degrees, where x is rounded up to the closest integer. Okay. So the sine of x, they're saying, is the same as the sine of x squared. So that means that x has to be equal to x squared. And therefore x squared minus x is equal to 0. So therefore x, factor it out, and then we get x is equal to 0 or 1. But they're saying the x has to be greater than 1. Okay, so neither of these are valid since, but x has to be greater than 1. Okay, so that didn't work. Okay, now not a problem. Let's analyze the sine graph. You guys remember the sine graph, right? It's cyclical. And this point here, of course, is 0. This is 180 degrees. This is 360, if I'm not mistaken. So, what does that mean? It means that if you analyze this graph carefully, you can deduce that if you have the sine of x, it's the same as the sine of 180 minus x, I believe. Let me think about this. So if you have the sine of this, it'll be the same as that. Yeah, I really hope that's right. So yeah, that makes sense, right? Because it's symmetric about the 90-degree point. So that means if you have the sine of x is equal to the sine of x squared, then that means the sine of x, this is the same as writing the sine of 180 minus x squared. So then we can just equate this guy with this guy. So x is equal to 180 minus x squared. And I think this should help us. Okay, so this is a quadratic, obviously. Put everything on one side. X squared plus x minus 180 is 0. Oh boy, this is a messy quadratic. So I'm not going to solve it. I'm just going to guess by plugging in values. If x is 12, this becomes 144 plus 12 minus 180, which is 24. No, it's minus 24. And if x is 13, this is 169 plus 13 minus 180, which is 2. Okay, so that means x has got to be between 12 and 13 in order for it to be 0. So x has got to be between 12 and 13. And if you therefore round up x to the closest integer, which is that symbol right there, it's 13. And I think that's what they're asking, right? What is x rounded up to the closest integer? Yeah, the answer is 13, and that would be B. For each positive integer n, let f at 1 at n be twice the number of positive integer divisors of n for j greater than or equal to 2. Let f at j at n equal f at 1 at f at j at 1 at n. For how many values of n less than or equal to 50 is f at 50 of n equal to 12? All right. So this is going to be very challenging, so I have to explain this very carefully. First, what we do is we try to understand what this question is talking about. Let's start with a basic example. Let's try f at 1 at n, and we'll use some n. Okay, let n equal, let's say n is 15. Okay? So 15, I'll just break it up into 3 times 5. So it's 3 times 5, and I put powers of 1 like that. Okay? Now, these numbers are very small, so we can just sort of figure it out on our own manually. So first I'll figure it out manually. How many divisors are there? Positive integer divisors, okay, of 15. 1, 3, 5, and 15. So there's 4. There's 4 positive integer divisors of 15, of n. And n is a 15 in this particular example. So therefore, f at 1 of n, which is 15, will be twice that. So 2 times 4, which is 8. So f at 1 at 15 is 8. So I hope you figured out, or I hope you understood how I figured that out. Okay, so now let's take it one step further and get into this recursive type of situation where now they figure out f at 2 of n, and n in our case is 15. Well, how do you figure out f at 2? Well, according to that formula, it's f at 1 of f at 1 of n, which in our case is 15. Okay? Well, f at 1 of this, well, this whole thing is 8, according to what we did. So now we got to figure out f at 1 of 8. Okay? So same thing. 8 has how many positive integer divisors? Well, what is 8, first of all? 8 is 2 to the power of 3, right? So we have 1, 2, 4, and 8. Is that it? Yeah, so there's 4. 4 positive integer divisors of 8. So therefore, since f at 1 of n is twice the number of positive integer divisors, it'll be 2 times 4, which is 8. Okay, so that's just an example of how to figure this out. Now, one thing I want to talk about before I get into the question is, how do you actually figure out the number of positive integer divisors of any number? Do you have to manually write them out like I did here? It's easy when the numbers are small, but once the numbers get a little bit bigger, manually writing them out is quite time consuming. So there's a quicker way. What you do is you take any number and you break it up into its prime factors. So let's say the prime factors are p and q. And then you make sure you put the exponents correctly. So p to the power of, say, whatever letters you want to use, a, and q to the power of b, right? Just like how I did up here. The number of positive integer divisors is a plus 1 times b plus 1. That's a very nice, simple formula that you can use. Now, I've only used 2 prime factors here because I want to make it simple. I don't want to get too complicated here because otherwise I'll lose most of you. But that's how you figure out the number of positive integer divisors. First break up the number into prime factors and then use the exponents to calculate the number. All right, so here we go. Here we go with the question. What they want you to do is figure out f50 of n equals 12, right? So how many values of n is this true for? All right. Well, we need to kind of go a little bit backward here. And let me explain. We have to understand that this recursive formula will go all the way back to f at 1, right? Using this formula up here. So this would eventually be something like this. It would be f at 49 at f at, it would be f at 1 f at 1 at f at 49 of n, like that. So eventually you're going to have to go backward. So because we have to go backward, we have to get some sort of understanding of what does a 12 give us. So let me explain. So if we have f at 1 of n is 12, what does that mean? How did we get 12? Okay, basically what it meant is that this n has 6 positive integer divisors, right? Because f at 1 is twice the number. So that means we have to find an n that has 6 integer divisors. And if that's the case, then f at n would be equal to 2 times 6, which is 12. Correct? Okay. So how do we figure out a number that has 6 integer divisors? Well, let's see. I actually just immediately looked at 12 and say, does 12 have 6 integer divisors? Well, what is 12? 12 is 2 to the power of 2 times 3 to the power of 1. Now, using that formula I showed you earlier, the number of integer divisors would be 2 plus 1 plus this 1 plus 1, which is 3 times 2, which is 6. Or if you want to do it manually, you can write them out. The number of integer divisors of 12 are 1, 2, 3, 4, 6, and 12. There you go, 6. So 12 works. If n is 12, then this formula holds true. Okay, but what about f at 2? f at 2 of n, which would be f at 1 times f at 1 of n. Let's see what happens here. F at 1 at f at 1 of n. F at 1 of n is 12 from up here. So put that in here. And then we have, again, f at 1 of 12 again. And we just figured out that f at 1 of 12 is the number of positive integer divisors of 12, which is 6, times 2, which is 12. So it seems like no matter what the iteration is, if 12 is the number, it's always 12 as an answer. So f at 3, which would be f at 1 of f at 2 of n. This is f at 1. F at 2 of n is 12. And there we go. We're right back to the same thing again. So 12 seems to be a recurring theme, meaning it's the same. So that means that we need a number that is either 12 or behaves like 12. So let me explain. In order to get this to work, we have to have an n that has 6 integer divisors right here. So that means since we are asked to choose an n between 50 and 1 inclusive, we have to choose an n that has 6 integer divisors. And that will be true if n is first, let's break it up into its prime factors, which let's say p to the power of a, q to the power of b. If we have this scenario, p to the power of 1, q to the power of 2, the number of integer divisors will be 1 plus 1 times 2 plus 1, which is 6. So we have to find all the scenarios that fit that. There's another scenario that if you just have p to the power of 5, then the number of integer divisors will be just 5 plus 1, which is 6. That's another one. So we have to now explore this scenario right here. And here we go. So the first one I'm going to concentrate on is this one right here. And since we are dealing with positive integers, we will start with the smallest prime, which is 2. Remember, 1 is not a prime number. So let's start with this scenario here. P to the power of a, q to the power of b. First scenario, which is q equal to 2. So this q right here. And we will start with this scenario first. So we have p to the power of 1, q, which is 2, to the power of 2. So this is 4p. All right? And our boundary is between 1 and 50, so we want 4p to be less than 50. And that will be possible if p is equal to, remember, p has to be prime, and it has to be different than 2, because 2 has already been used. So the next prime we can use is 3, 5, 7, 11, and 13. And that's it. So when we do that, the values we get for n would be, let's see here, n would therefore equal 12, 20, 28, and 44. Okay, so we got a few so far. We got 4 so far. And what are the answer choices? 7, 8, 9, 10, 11. Okay, so we got to find obviously some more here. Okay. All right, well, that's a pretty good start though. We found 4. Now I guess we have to go and see what happens if we choose another prime. So we've chosen q equals 3. Q equals 2. Let's try q equals 3 now. If q equals 3, now n is p to the power of 1. Again, we're using this scenario. And now 3 to the power of 2. Like that. And we can therefore experiment just like we did here. If this is less than, this is like 9p, and we want this to be less than or equal to 50. So we can get that for p equals 2 and p equals 5. And I think that's it. So that would give us values of n would be 18 and 45. Okay. And then similarly, you just keep going here. If q equals 5, you have n is equal to p to the power of 1 times 25. And the only way you're going to get that less than 50 is if p is equal to 2, and therefore n would be 50. And I think if you experiment with this a little bit more, moving up, choosing values for p, if p is equal to 3, then we get 3 to the power of 1 q squared, and the only way that's going to be less than 50 is if q is 2 or q is equal to 5, which would get values of n of 12 and 75. Well, that's outside the range, so I guess we're done. So let's see, let's circle the ones that worked. This one worked, that one worked, 50, that one worked, and I think 12. So how many did we get? We got 4 over here, and then we got another 4 here. So we got 8. Is 8 one of the values? Yeah, it is. But this question's hard because that actually doesn't complete everything. We still got a couple more, believe it or not. Actually, the first thing I noticed is we actually didn't get 8, we got 7 because 12 is included twice. Where you actually get the 8th value is by looking at this scenario right here, the p to the power of 5. The only number for which we get n less than or equal to 50 if n is equal to p to the power of 5 is if p is equal to 2. And that would give you 2 to the power of 5, which is 32. And 32, therefore, is the next value of n that we can add to our list. Now we get into the final two. And the final two are very, very tough, I think, for someone to figure out. And we have to look at the recursive formula, f at 50 is equal to something that would give us eventually something that comes down to 12. And let me explain, because 12 seems to be that magic number that it always will be 12. And after experimentation, you find that it's actually 36, because 36 is what? 2 to the power of 2 times 3 to the power of 2, right? So the number of divisors would be 2 plus 1 times 2 plus 1, which is 9, right? So that means that this would be 2 times 9, and that's 18. And then you'd put the 18 here, and then once you figure out this is 2 to the power of 1, 3 to the power of 2, the number of divisors are 1 plus 1 times 2 plus 1, which is 3 times 2, which is 6. So this is 2 times 6, which is 12. So you arrived at that magic 12, but you got there by putting 36 in there. So 36 is another value of n that will work. And then with similar experimentation, you find that when you put 48 in there, you eventually also get down ... to a scenario where f at 49 would be 12. And I'll let you do that. It's fairly straightforward. So after a big long song and dance, we got 36 and 48. So we have 1, 2, 3, 4, 5, 6, 7. This has already been counted. 8, 9, and 10. So 10 is the answer. And therefore number 23 is D.